Oh, no wonder this is weird. Okay, so 1.4 exponential functions. And this, oh, there's a few notes that I forgot to go over. So once again, the exam is Thursday, Friday. The submit button in Webassign, a lot of you figured this out, that the submit button doesn't do anything. I'm talking about the submit button at the bottom. So each homework exercise has like a submit button, and you submit those, and then you see the But once you've submitted those, once you've hit those submit buttons and gotten and looked at each homework exercise, then the button at the bottom of the page, which says, the button at the bottom of the Webassign homework page, which says submit assignment, that really doesn't do anything. And so once you get a green check mark on all the parts of the problems, then you've pretty much, then it's basically that assignment is submitted. Okay, that assignment is updated. So whatever green check marks you have, those are counted already. And also just a reminder that if you don't have a 100% score on a homework and you want to get 100%, then you could request a homework extension. And you do that by going to the past homework assignments, and then on the homework assignment that you like extended, you click request extension, and then you put in a date and a reason. Okay, so exponential functions are of the form f of x equals b to the x, and b is a constant in this case. So the b is fixed, but the x is a variable. And to graph those, what I generally do, and we'll get to that a little bit later on how to graph those, but I generally start by graphing these 2 points right here. So, so if your f of x is your y and your x is your x is your x, then when x is 0, if you plug that into there, then you're going to get b to the 0, which is just 1. And when x is 1, you get b to the 1, which is just b. Okay, so it's going to go through those 2 points no matter what, if it's of this form right here. And so that's a good place to start with in graphing it. And then I'll tell you later about what the general shape is going to be. Okay, there are some laws of exponents that you should have already memorized and be able to use them backwards and forwards, right and left, up and down. So b to the x plus y is b to the x times b to the y. And this is because b to the x plus y, basically what it is just a bunch of b's multiplied together x times, and then bunch of b's multiplied together y times, or x plus y times, and then you just have x times, and then that's how that works. Okay, so those are going to be the same. X minus y would be b to the x over b to the y, and then b to the x to the y is just going to be b to the xy. Okay, so the power here is a multiplication. The adding here is two separate ones, and then a times b to the x is a to the x times b to the x. Okay, so just a few things to remember. Okay, with the exponential, there is what we call a natural base. Okay, so here b is the base of the exponential. Okay, so b is the base. And there's a natural base, which is the number e. And as we'll find out later, the two basic shapes, if b is greater than 0, then there's this one. And if b is greater than 1, okay, so if b is greater than 1, then it's like this. If b is between 0 and 1, then it's like this. Okay, so those are the two basic shapes of the exponential. And so E is about 2.7 something, and so E is going to be like this. It's going to be the first one. And at this point, 0, 1, like I said, this point's always on the graph. The slope of, like if you draw a tangent line at that point, that slope is going to be exactly 1 for this one, okay, for y equals e to the x. This is kind of weird because like this textbook defines it that way, defines e to be that number, the number that does that. Whereas there's actually a lot of different ways you can define e. Let me just give you an example. So for example, and it's this number here, 2.71828. It's irrational, goes on forever. Like you could define it as, you could go 1 plus, well, there's a pattern is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. And that turns out to be, well, that's this infinite sum or infinite series, and which converges to E. Or basically, it's kind of like that sum is actually going to be E. Okay, you could also define it like this. If you took this kind of expression right here, and you took the limit as n goes to infinity, so as you make n larger and larger and larger and larger and larger, then it's going to converge to this number here. Okay, so there's like different ways that look like they're independent of each other that you can approach this number right here. So that's why this number is important in mathematics. And it's as far as the exponential, E is the natural base. Among exponential functions with different bases. Okay, so E is the natural base. Okay, so let's get into the homeworks, and let's look at. So the first one, we're going to do a little bit of this stuff right here. That's the first exercise. Okay, so the first one is to simplify this, and we're using the last property that I mentioned there. So this quantity raised to the 7th, that's going to be 2 to the 7th times b to the 7th. Okay, and then the 2 to the 7th is 128. And then these two, you combine those and add. So that's just using the properties from the first page. So 128 times b to the 15th, that's the answer to the first, to 1a. Okay, let's go to the next one. And just like, for that one, I just used this property first, and then I used that property right here. Except I had this, and I went from here to here. Okay, so I had this b to the 8th times b to the 7th, and then they put it turns into b to the 8 plus 7. Okay, so let's go ahead and do this one. So that's going to be, so quantity raised to the 4th, that's going to be the first one raised to the 4th, and then y cubed also raised to the 4th. And then down here, we just have 2y cubed still. Okay, so 6 to the 4th Well, let me just illustrate that it's 6 times 6 times 6 times 6 is what it is. That's what 6 to the 4th is. And you have this 2 here. And then this quantity right here is y to the 12th. Okay, so I'm using this property here, where you have a power, you have some number raised to the x, then all that quantity raised to the y. Okay, so you have all that quantity be raised to the 4th. So this is y cubed, all raised to the 4th power. That's y to the 12th. Okay, and then we still have the y cubed there. Okay, now this 2 is going to cancel, is going to reduce part of this to 3. One of those to a 3. Okay, and then we have y to the 12th divided by y to the 3rd. That's going to be y to the 12 minus 3. That's what that does. And then let's see, 6 times 6 times 6 times 3. That is 648. Okay, so 648 y to the 9th. Okay, so just using the property of that last one, that y to the 12th or y to the 3rd, I use this property here. Or should I started here and went that way? Okay, so does anybody have any questions about anything? Okay, let's go to the next exercise. Write an equation that defines the exponential function with base b, where b is greater than 0. Okay, and that one's just going to be f of x equals b to the x. So it's an exponential function with base b. Okay, domain. Domain is going to be everything. But you can put negative numbers in here. If you put a negative number, then it's just 1 over b. The range is going to be from 0 to infinity. As long as b is not equal to 1. If b is positive, then the range is going to be from 0 to infinity. That's because if you start with a positive number and you raise it to a power, even if you raise it to a negative power, you're still going to have a positive number. Okay, so here we want to sketch the general shape of the graph for each case. So what I said before was you're going to, when x is 0, it's b to the 0, which is 1. And when x is 1, it's b to the 1, which is b. So in this case, when b is greater than 0, what's going to happen is if you plot 0, 1, right, there's 0, 1.
Wait, I'm sorry, I have a quick question.
1. Yeah, go ahead.
About letter C, if b is not equal to 1, what's the range of the function? Oh, it's the range. Okay, I was thinking it said domain, so I was wondering why it wouldn't be negative infinity to 1 and then 1 to infinity, but I missed the part that said range.
Yeah, well, even if b is not equal to 1, the domain goes from negative infinity to infinity. The domain includes 1. Because the domain is the x values. It's not the b values, it's x values. Okay, so x can be anything. Okay, so now if b is greater than 1, that means that b is going to be up here somewhere above. So we'll say maybe b is right there, which means that when you plot this point, you're going to be right there. And the rest of it goes in like this. And then this goes up. Okay, so that's when b is greater than 1. And so you can see here from this, the range is the y values. There's 0, but it's going to hit everything above 0 all the way up to infinity. All these range of values, but nothing in the negative part. Okay, if b equals 1, then you basically just have, then your function is this. is just 1 to the x, which is always just going to be 1 no matter what x is. Okay, and so then your graph's just going to be a horizontal line at 1. Okay, and then if b is between 0 and 1, then again, going off of this right here, I'm still going to go off of that. Here we have 0, 1 right there. But if b is between 0 and 1, instead of being up here, b is going to be down here somewhere, maybe right there. And so then you're going to go through that point. So that point and that point on, and instead of going up, it's going to go down. It's just going to go down faster. It gets close to this down here pretty quickly, by the way. So I just can't bring myself to draw that. Okay, there's something like that. It gets really close to the x-axis pretty quickly. And you can see that on the homework. You can see that on the homework exercises, that it just like pretty much, it looks like it just goes down and touches the x-axis. So the direction doesn't actually touch it ever, but it looks like that. It gets close enough that it may as well just be touching, right? Okay.
Why does it change the, I mean, like, why does it, what was that, like, reflect it? If it's less than 1 and but greater than 0, wouldn't it still be a part of, like, because if I don't know, if b is greater than 1 and 0 would be 1 and 1 would be b, like wouldn't that same point would still be there? Why does it I guess what I'm saying is on the left side, the reason why it curves up on the right and then it curves down on the left, because you're kind of like following the slope, right? If it was less than 0.
Wait, oh, so you're saying why does this one come down and why does this one go up?
Yeah, exactly. When it yeah. Because wouldn't what's on the left side be, well, I guess that would just be it'd be what's left, no. I don't know, I'm kind of confused. Because you have plotted right here the 0, 1, 1b, and that came up with this green graph here, right? You used that to come up with the green graph. So why is that? Isn't that between 0 and 1 right there? Or I guess that's for the x value, huh?
Let me see. Let me do this, okay? I think I can illustrate that point with exercise number 4. So we'll skip number 3 for now. We'll come back to it. So there's number 3. Here's number 3. We'll come back to that in a minute. But let's look at number 4. Okay. And I think I can answer that. I think you can see better with number 4 what's going on. Or maybe we'll talk about number 4 and then we'll come back to what's going on. So here we have these 4 graphs. And it turns out that this one and this one are reflections of each other through the y-axis. Okay, and we'll go ahead and graph these. Now to graph it, let's see here. Let's go to GeoGebra. So I like to use the same program. So you go to geogebra.org and go to the graphing calculator. And the 4 graphs that it asked for was y equals e to the, no, 5 to the x, and then y equals 10 to the x, and then y equals 1/5, No. One-fifth to the x, and then the last one was y equals 1/10 to the x. Okay, so those are the 4 graphs right there. And so the green one and the red one, which is 5 to the x and 1/5 to the x. So that one and that one are reflections of each other through the y-axis. They're mirror images of each other through the y-axis. Okay, so just look at that on the graph. I'll try to explain why in a minute. But and then also the blue and the purple one. So these two, those are reflections, also reflections of each other through the y-axis, because one of them is 10 to the x and one of them is, the other one is 1/10 to the x. Okay, so just look at that. Let's answer the questions, and then I'll come back and try to explain why those are reflections of each other. So the functions with bases greater than, so I'm going back to the Webassign. So if you've got your Webassigns open, the functions with bases greater than 1, so that would be this and this one, these two are increasing. Okay, so those are increasing. The other two are decreasing. So the answers are increasing and then decreasing. And then the graph of 1/5 to the x is the reflection of 5 to the x about the y-axis, and the 1 to the 10th x is a reflection about the 10 to the x about the y-axis. The graph of 10 to the x, which is this blue one, increases more quickly than 5 of x for x greater than 0, and approaches 0 faster as we go to negative infinity. So the blue graph, as you go this way, the blue graph's approaching 0 faster than the green one. It's below the green one. Okay. So so let's go back to the PDF reader and go back to the PDF document. Okay, so the answers are increasing, decreasing, wait, and then y-axis, y-axis, and then x greater than, and then x goes to negative infinity. Okay, so those are the answers. Just what we explained there. Okay, so what happens is, let's take like these two, for example. Okay, so let's take y equals 5 to the x. Okay, so what happens is, let's say that's the value of x right there. Okay, now y equals 5 to the negative x is the same as 1/5 to the positive value of x. Okay, so the negative in the exponent you can get rid of that negative by changing this to 1 over whatever it is. So instead of a 5, it's 1/5, and that gets rid of the negative. Okay, so that's kind of how negatives work. So the negative means you take the power without the negative, but applied to 1 over that. Okay, so that means that if you're over here at negative x, okay, then that's gonna go. What the drawing is so bad. I mean, that's why it's gonna be a reflection through the y-axis of the other one. So any point over here, when you take the negative value of it, that's the value that you're going to get for the other one. Okay, hopefully that gives you some little bit of an idea. And if you think about it, maybe that will help you further.
Yeah, that makes a lot of sense. Thank you.
Okay, great. Thanks. Great. Okay, so let's go back to number 3. And then the first part is, how is the number e defined? And we said it earlier, it's the value such that will make the tangent line at 0, 1 have. So tangent line of y equals e to the x has slope 1 at the point 0, 1. So that's how they define it in this book, which is like, this is the first time I've ever seen any math book define it that way, by the way. But it works, of course. Okay, so b, what's the approximate value? And that is 2.71828. Okay, and then what's the natural exponential function? That's just going to be well, f of x equals e to the x, or it could be what they say, y equals e to the x. Okay, that's the natural exponential function. Okay, so number 5. So here we're supposed to make a rough sketch of this right here using transformations. And they kind of start us off with this right here, that because e is approximately 2.7 something, that means it's between 2 and 3, but closer to 3, right? So that means that the function y equals e to the x is going to be between y equals 3 to the x and y equals 2 to the x, but closer to y equals 3 to the x. Okay, because e is between 2 and 3. That's how that is. Okay, now here, it might be better if you look at it this way. And then you start to pick this apart and say, okay, what does that, so we'll start with the x here. What does this minus right here do? Okay, so I think it was last week, that we talked about transformations of functions. Okay, so what you should think about when you see this is, you should think this. Okay, so e to the x is your original function. It's e to the x right here, original function. And so e to the negative x is f of negative x. And then you're multiplying outside. So this is inside. You only have a not minus x inside. Outside you have multiplied by negative 1/2 and then adding 1. Okay. So the negative inside, this will this is going to be, so the inside stuff, remember, is horizontal, and this will reflect it through the y-axis. This is multiplied by negative is a reflection. Okay, so perhaps we should illustrate that here. So here you have the 1. Here you have the e to the x. It's going to be reflected through the y-axis. Okay, so that's going to be like that. So that's y equals e to the negative x. And it's also similar to what we just, this is another way to look at this right here, why the reflections are. The minus is, it does that, is minus is that. Okay. Okay, now this negative 1/2 here. Well, the 1/2 is going to shrink it because it's vertical now. It's going to shrink it, and then the negative is going to flip it over the y-axis. So once again, this is reflection through the y-axis. Okay, then this part right here, we're going to be reflect through the x-axis because that's negative, and shrink by 1/2. Okay, so that's going to be, so you're going to reflect this through the y-axis. So instead of being at 1, you're going to be at, this is going to go to 1/2. So that's 1 there. This is going to go to 1/2. Well, it's going to negative 1/2 because it's reflected. I'm trying to do two things at once. So it's going to be something like that. So that would be negative 1/2 f of negative x. And then finally, this last part, that's going to shift it up by 1. Okay, so this minus 1/2 goes up to here. Minus 1/2 goes up to the plus 1/2 there. And this, so the exponential functions, just the raw exponential functions. So like if you, like 3 to the x, 2 to the x, e to the x, they have a horizontal asymptote along the x-axis. Okay, so that horizontal asymptote here is going to be shifted up to 1. Okay, so y equals 1. Okay, so that's just going to go like that. Okay, so that's what the final answer should look like. This one right here. So for me, that's the second to the last one. Okay, any questions on that? Okay, let's move along to number 6. If f of x equals 9 to the x, show that, okay, this is the difference quotient. So I found that one of the most difficult things for people to deal with is the difference quotient. But it's pretty straightforward, or should be pretty straightforward, okay? And so this problem is to kind of help you through the steps. So essentially, you're just substituting everything. So here's your function. So this right here gets substituted to 9 to the x plus h minus 9 to the h. No, 9 to the x. Okay, and then it's all over h. So this one gets replaced by that. This gets replaced by this, because that's what the function is. And then the h just stays the same. Okay, so that's the first step. And then you use the property of exponents to where this x plus h is 9 to the x times 9 to the h, like that. And then you can factor a 9 to the x out. And then, of course, this factors all the way out. You could just factor it all the way out like this. Okay, So that's the number 6. Okay, just let me know if you have any questions anymore.
Yeah, sorry, okay, so it's, so the first step is gonna be, yeah, I'm kind of, I don't know why, but I always have, I always have trouble with like figuring out where things get substituted. That's kind of what confuses me. Can you, okay, so can you just really quick explain just the first step again?
Yeah, okay, so f of x is 9 to the x, right? So f of x plus h, okay, this x got replaced with an x plus h, right? So then this x is like, hey, you have to replace me also, right? I also want to get replaced with as an x plus h. So that's that, right?
Oh, okay.
Okay, now, so that's going to go here. And then, of course, f of x is just 9 to the x, so that goes, so minus that. Okay?
Okay, that makes sense.
So it's just like substituting each, so that is this substitution right here. So that's this replacement right there. Okay. So this is going to happen a lot. So it's good if you practice it a lot and then get it down right. But it's pretty straightforward. I think though that you need a lot of experience with this. It's not that difficult, but you need experience.
Wait, really quick, just the very last step. How did you go from 9 to the x over h? Like, how did you isolate that from? Like, I see how you factored it out and like how you rearranged that on the top, but the very last step, how did you like basically cancel out the h that would have been under 9 over h, 9 to the x over h?
The h is still there. The h is still right here.
Yeah, but wouldn't the
So
h have
if
to
you
stay underneath? Sorry.
okay, so if you have, let's say you have m times n over k. Okay, so just any like 3 numbers or whatever. You can pull stuff out of the numerator and just all the way out like that. You can pull, it's just a different way of writing it.
Oh, okay, because that's technically m over 1, which you could multiply, and then is that why?
Yeah.
Or m over m, which could then, yeah. Okay, that makes sense.
So this is how the rules of multiplication work. So multiplication, and if you have multiplication and division, you can multiply these two together and then divide by the k, or you could take the n and divide by the k and then multiply that result by the m.
Okay.
Those will give you the same. Those will give you the same answer. Just the properties of that. Okay. So you do have to be careful with the denominator though. But yeah, but this is perfectly fine. Okay, so let's look at number 7. And it's kind of an application. The half-life of bismuth 210 is 5 days. Okay, so I'm going to skip down here to part B and just show you how you can come up with that. So half-life means that in 5 days, the amount that there is going to be cut in half. Okay, so that, or actually, let's just go through part A. So you have 232 milligrams, and you're supposed to find out how much is going to be there after 15 days. Okay, so at the beginning, you've got 232 milligrams, right? Now, after 5 days, that's going to be cut in half. So you're going to have 116. Okay, because the half-life is 5 days. That means every 5 days it gets cut in half. Okay, then after 10 days, that's going to get cut in half. So you're going to be down to 58. Okay, but you cut that in half. And then 15 days, that's going to be cut in half. So you're going to be down to 29. Okay, so 29 is going to be the answer to the first part. Okay, so any question about that? That's kind of how half-life works. It's not like, yeah, I'm sure you've heard of that before, and you're a little bit familiar with half-life. Okay, so part B, they want you to come up with like a general formula for how this works. And you can use exponential functions to do that. And I will just show you how you can do this. Okay, so 232, that's your initial amount, right? And then if you want to incorporate a half-life of 5 days, then you multiply this 232 by 1/2 to the t over 5. Okay, so think about it. So this is the formula that's going to work, but think about why it works. If I put a 5 in for t, then this is a 1. So it's 232 times 1/2, which is going to be 116. If I plug a 10 in, then I get 10 over 5 here, which is a 2. So I got 232 times 1/2 squared, which is 1/4, which is going to give me the 58. And then if I put the 15 in, this is going to be a 3, and that's going to give me 29. Okay, so that's why this formula works. Okay, part C, it says estimate the amount remaining after 2 weeks. Round to 1 decimal places. Okay, so I think what they wanted you to do here is just kind of graph this and then look and see what happens at 2 weeks. Or actually, no, wait, no. I'm sorry. You can just plug in 14. Okay, so when you plug this into the calculator, be sure to put parentheses around that. Otherwise, it will do the operations out of order. And I get approximately 33.3 milligrams. Okay, so 2 weeks, that's 14 days. And so you convert that to, so this is in terms of days. Okay, so 33.3. Okay, then part D, estimate the time required for the mass to be reduced to 1 milligram and round to 1 decimal place. Okay, so this is more difficult because you want to see when that's going to be 1 milligram. Okay, so I think what they want you to do is kind of guess around, but I'm going to show you how to do it like a more straightforward way, because that's going to lead into what we cover in class tomorrow. Okay, so, and some of you, I'm sure, are familiar with logarithms. So essentially, you isolate this exponent over here by taking this, dividing this 232 to the other side of the equation. Okay, and then what you're going to do at this point is take the natural logarithm of both sides. Okay, so if you don't know what this is, that's fine. We'll talk about that. We'll talk about it tomorrow. But that's what it is. Okay, so the logarithm is basically the inverse of the exponential function. And because of the properties of the exponentials, the properties of logarithms say that we can bring this 2 over 5 out in front, like that. And then you can solve for t that way, by dividing by log of 1/2 and multiplying by 5.
Can you scroll down a little bit? It's hard, I can't see it. Part of the screen's blocked off.
What? The part of the screen is blocked out. What? How?
Mine just where the bar is for like the mute, start video, and all that. It's blocking just a very little, like maybe like half an inch of the screen. I just can't see what you wrote underneath the natural log of 1/2 t to the 5 equals natural log of 1 over 232.
You can't see this down here? Wait.
Yeah, it's out of my screen. Like it's too low, just a little bit. If you could just like scroll up a little bit, I don't know.
Dang, I can't scroll. So can you see t over 5 log of 1/2 equals log of 1 over 232?
Yeah, I can see that. I just can't see what you wrote right below that, right before you got to the t equals 5 natural log of 1 over 232 over
Wait,
natural log of
can you
1.
see this stuff? Can you see this?
I
I'm
can't see
circling?
that. Yeah, no.
You can't see that. Okay.
I'm trying to figure out a way to.
Okay, so I'll also put it here. So what happens is this,
Okay, I fixed it on my end. That's it's just my computer.
okay, well, be sure to discipline your computer later. Okay, so anyways, this t over 5 comes down, right? And then the 5 goes up here, and the log of 1/2 goes down there, right? And so you get this. And then you can put this into a calculator or something. You can put it into GeoGebra. I think you could easily do that. And your answer is going to be about 39.3. Okay, and then finally, this last one, use a graph to estimate the values of x such that e to the x is greater than this really big number. What is it, 1 billion? Around to 3 decimal places? Bigger than 1 billion? Okay, so what I did for that one. Okay, so I went in and I went and used the GeoGebra and I graphed, let me just tell you what I did, okay? I graphed y equals e to the x, and I graphed y equals 1 billion in GeoGebra, and then I had to zoom way out to where I could see. So this one's going to be like a horizontal line. This is really high though, and this is going to be e to the x. I had to zoom really out really far. I wasted like a minute zooming out, and then I wasted another minute trying to zoom back in, and then somehow it just like got off the screen. I could click and see it said the intersection point was like something that I knew it wasn't. And then when I zoomed back in, then it kind of went off. I lost track of the center. I lost track of the intersection and was just left with blank screen. So then I said, forget that. I tried another online calculator, Desmos.com, and this one gave me, I could actually, it made me zoom out also, but when I zoomed out and clicked on the point, it showed up as 20.72, comma, and then the billion, whatever, like that. But then it's requiring 3 decimal places, so I just started guessing at the decimal place, and I guessed it, and I finally guessed it. It's 2.723. Okay. So that's how I did it, because they're saying to use graphs, but it's probably better if you just do this and then take the natural log of both sides. And the natural log is the inverse of the natural exponential function. So that's going to be that. This will be where these are equal. So then it's just a matter of plugging in the natural log of 1 billion in your calculator. And that is approximately 2.723265 8.